So today's topic for discussion is diamond cubic crystal structure. So in last lecture we have seen hexagonal close packed crystal structure where there was hexagonal Bravais lattice plus 2 atom bases. So in this diamond cubic crystal structure also the motif or basis consists of 2 atoms. Many crystals or many materials like carbon in diamond form, semiconductors like silicon, germanium, then alpha tin, a non-metallic form of tin, these are all crystallized in diamond crystal structure. One important point it is better to note at the very beginning is diamond cubic is a term used to represent crystal structure. The Bravais lattice which come in diamond cubic crystal structure is face-centered cubic Bravais lattice. So there is nothing like diamond cubic Bravais lattice or diamond cubic lattice. Diamond cubic is a crystal structure which use face-centered cubic Bravais lattice. So in face-centered cubic Bravais lattice, the atoms locate at the corners, then on the faces, each of the 6 faces, and there are 4 atoms per unit cell. So in diamond cubic crystal structure, 2 face-centered cubic Bravais lattice, of which one is pushed along the body diagonal by 1/4, 1/4, 1/4. So then we get a new structure, that is diamond cubic crystal structure. So in diamond cubic crystal structure, there are 2 interpenetrating face-centered cubic Bravais lattices. One face-centered cubic Bravais lattice is pushed along the main body diagonal by 1/4, 1/4, 1/4. So let us visualize in another way. Suppose we have got 2 tightly packed cubes. Here we have one cube and inside there is another cube which is I mark in red color. Now one of these cubes, here there is a common origin, I marked it A, that is 0, 0, 0. So this base plane I mark it as A, B, C, D. So along this body diagonal, so this A is bottom, back, left corner, that is taken as origin, and this is top, front, right corner. So this point I call it small a. So this A to A, this is a body diagonal. So if I mark, this is a body diagonal. So along this body diagonal, suppose we push one of the cubes. If one of the cube is pushed, both these cubes are face-centered cubes. So I redraw. So here we have one cube, and along the body diagonal, this is A, this is your body diagonal, this is half, and somewhere here is your 1/4. So 1/4, 1/4, 1/4. That is along x, y and z directions, it is 1/4, 1/4, 1/4 cube edge. So if we push this red cube in that direction, then red cube will be coming here. So something like this, red cube will be little push outward. So if we take these different faces, so here this black cube I am giving these corner atoms, and there are face-centered atoms. So here there is a face-centered atom, here one is there, here one face-centered atom, here one face-centered atom, the black back face there is a center atom, and the front face there is one centered atom. And on this red again it is another face-centered cubic lattice. So there will be atoms at the corners, then also on the face center. And back and front. So in this case, when this cube is moved along this body diagonal, when it is coming forward, then the front face is coming out of this black cube. Similarly, this right face is also going out of the black cube. Top face is also going out of the black cube. So altogether, after when we move this face centered or second Bravais lattice is pushed through along the body diagonal by 1/4, only these atoms, only the atom which is at this corner, this face is coming out. So this no atom inside. Only this atom, this corner atom which is behind, that is back corner atom, this left face center atom, bottom face center atom, and back face center atom. So here this is back face. So this back face center atom, only these 4 atoms. 4 of these atoms attached to this red Bravais lattice are within this black cube. So within the black cube now we have, there are 8 corner atoms, 6 face atoms or face center atoms, and there are 4 additional atoms coming from second Bravais lattice. So this is how we are getting diamond cubic crystal structure. So in this, if we analyze, each one is a face-centered cubic Bravais lattice. So in face-centered cubic Bravais lattice, there are 4 atoms. In any face-centered cubic Bravais lattice, there are 4 atoms. We mark it as lattice positions 0, 0, 0, half, 0, half, then half, half, 0, and 0, half, half. And these 3 units, that is half, 0, half, 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 0, and 0, half, half, they are known as phase centering translation. By repeated application of this phase centering translation at any lattice point on this black cube, we will be able to reproduce all, or we will be able to reach all the lattice points associated with black cube. Similarly, if we apply these phase centering translation to any of these red lattice point, then we will be able to reach all red lattice points. But by repeated application of these phase centering translation on the lattice points associated with black cube or this black lattice site, we will not be able to reach this red lattice site. Here, suppose we are giving a translation of 1/4, 1/4, 1/4 at this origin. If I give a lattice translation of 1/4, 1/4, 1/4 at this origin, we will reach this position. But that cannot be considered as a lattice translation, because if I give additional one more translation 1/4, 1/4, 1/4, we will reach a position well inside the cube. That will be at half, half, half. That is exactly the body center of this cube. But at the body center of the cube, there is no lattice site. Therefore, this 1/4, 1/4, 1/4 is not lattice translation. It is just this one face centered cube is shifted along the body diagonal by 1/4, 1/4, 1/4 of the cube edge, or a/4, a/4, a/4. So that is not lattice translation. So lattice translation is only this one, half, 0, half, 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 0, and 0, half, half. That means this red cube and black cube, they are totally independent lattice structures or lattice face centered cubic lattice. So this type of system is what we call it interpenetrating face centered cubic lattice. 2 face centered cubic lattices, one is pushed along the body diagonal such that the origin of the second one is at 1/4 position with respect to the 1/4, 1/4, 1/4. 1/4, 1/4, 1/4 position with respect to the origin of the first one. That is how we get diamond cubic crystal structure. So in the case of diamond cubic crystal structure, there are 2 sets of lattice positions. So these 2 sets of lattice positions associated with 2 different face centered cubic Bravais lattices are chemically identical but not equivalent. That is what we have seen. Chemically identical means all these lattice positions are attached with same atom. In diamond, all are carbon atom. If it is silicon crystal, all are silicon atom or germanium atom. So, these lattice positions are chemically identical, but they are not equivalent. They are not equivalent in the sense we cannot move from one lattice position to another lattice position by giving this lattice translation operation. Therefore, they are considered as two independent separate lattice positions. That is how we get diamond cubic crystal structure. This is one approach. Because when we talk about a crystal structure, we can speak either in terms of space lattice or in terms of unit cell. That is, crystal structure is formed by space lattice as a whole with bases attached, or we can take it in the form of unit cells, which when packed together, we will be getting crystal structure. So, this is one approach or one way we can try to visualize diamond cubic crystal structure. So, these lattice sites will be attached with bases. So, when basis is attached, we will be getting crystal structure. Now, in order to understand this better, we have to work out with the help of unit cell. That is, unit cell means it is the basic structural unit which when repeated in three-dimensional space, so we will be getting the complete crystal structure. So, what is the unit cell of diamond cubic crystal structure? Diamond cubic crystal structure is having a cubic unit cell. So, unit cell is purely a cube. So, we will try to see. So, a diamond cubic unit cell is a cubic unit cell which is having lattice position or atom positions 8 corner atoms, 6 face-centered atoms and 4 atoms of the second face-centered cubic lattice which is also available within. That is, there are 8 atoms at the 8 corners, 6 atoms on the face centers and 4 atoms of the second lattice which are coming inside. But when we mark these 4 atoms of the second lattice, as far as this face centered cubic unit is concerned, that is not part of the cubic lattice. Because these 4 atoms, they are well inside. One is at 1/4, 1/4, 1/4. We have to locate the other one. So, those 4 atoms are not exactly at the lattice site. So, therefore, what we have to do is we have to attach those atoms to this lattice position. Then that is how we get this basis. Basis consists of 2 atoms. So, in this case, the first atom, I call this point A, B, C, D. This is small a, this is bottom back corner, this is top left corner. So, this is also B, so that this form a body diagonal, this form a body diagonal, this is front and this is back. Therefore, this is D and I take this as small d and this is C, I take this back, so this is small c. So, this CC is a body diagonal, BB is a body diagonal, AA is a body diagonal, DD is a body diagonal. So, if I mark like this, so this is one body diagonal, this is another body diagonal and this is another body diagonal and one more body diagonal comes here. So, on this first atom, that is we are pushing the one face centered cubic Bravais lattice up forward, that is from the back bottom corner we are coming forward. So, the 3 faces of the second face centered cubic lattice come out of this cube and 4 atoms of the second cube comes within this. So, here one is coming at this 1/4 position, somewhere here there is a 1/4 position. At that 1/4 position we have the origin of the second cube, that is 1 atom position. So, when we have one atom like that, imagine this is our bottom face of that other cube. If there is a bottom face of the other cube, its one corner point, this corner point is coming here. So, naturally the other atom, this face center atom will be half unit forward and half unit rightward, because face center is at half half. Therefore, exactly on this same plane we will have one more atom, but that will be half a unit forward and half a unit like this. So that atom will come, if you carefully analyze, that atom will be coming on this C diagonal at 1/4. So this is halfway, this is 1/4. And the other atoms which is here we have one and one face is coming here. So when this cube is moved forward, one atom is on this face center, that is also within this. So that one is at, again from here you have to move upward half unit and forward half unit. That will be at 3/4 position. And the other one is on DD diagonal. So you will be having 4 atoms. Carefully if we analyze its location, these 4 atoms will be on the body diagonal. These 4 atoms will be on the body diagonal, and if we take this base plane, and from this base plane if you draw 4 diagonals, these atoms will be on cyclically at 1/4, 3/4, 1/4 and 3/4 from these corner points. That is, from A there will be an atom at 1/4 position, from B there will be an atom at 3/4 position, from C there will be an atom at 1/4 position, and D there will be an atom at 3/4 position. So this is the diamond cubic unit cell. So diamond cubic unit cell is having 8 corner atoms, then 6 face-centered atoms, and 4 atoms within the cube from the second face-centered cubic lattice. So altogether you have 8 into 1/8 because only 1/8 contribution. Here 6 into 1/2, only half because it is shared between 2, plus additional 4. So total we will be having 1 plus 3 plus 4, so total 8 atoms per unit cell. So diamond cubic unit cell is a cubic unit cell which is having 8 atoms per unit cell. So in order to visualize, this is the isometric view of diamond cubic unit cell. But we want to attach this. This is not a possible lattice position as far as this face-centered cube is concerned. Therefore, these atom positions or these atoms are to be attached to these lattice. Then only we can say that there are, or each lattice is having 2 atom bases or motif. So in order to attach this, we will try to visualize this in a different way. Or we will take a 2-dimensional projection of this cube. Suppose we take a photograph from above. So all these atoms will be seen on this AB plane or ABCD plane. So that bottom 2-dimensional plane. So we will be getting a projection. So we will try to draw that 2-dimensional projection to understand how we can attach these atoms to the lattice site. So I draw this ABCD. So this is ABCD. So I take, this is A, this is B, C, D. So this A I have marked here, B I have marked here, C here, D. So this is nothing but this bottom plane. So these bottom planes are having 4 corner atoms and 1 face-centered atom. Now we are taking the projection. So this is, for the timing I take this as X direction and this as Y direction. So that is AD is X direction and AB is Y direction. So this direction is Y. So Z direction we are not showing here, so that is vertically above, they are coming on the bottom plane. So in this case, this one, the other one, those other atom positions which are coming from the projection are going to be marked with red. So in this case, this one will be just above this AD line. So it will be exactly on AD midpoint. So AD midpoint you will be having 1. So this atom is actually it is half unit above XY plane. So this is, I mark it as half. Another is, this one is coming here. So that is also, that is on BC line. So here there is one, that is also half unit above. Then another is back plane, one will come here. So that is also half unit above. And this point also will have half unit above. And these 4 atoms, this is at 1/4, this is at 1/4, this is 3/4, this is 3/4. So this one will be, these 4 atoms will be coming at points here. So one is 1/4 is coming close to A. From A there is at 1/4 distance 1. From B 3/4 distance 1, that is here. And from C 1/4 distance again there is 1. And from D 3/4 distance there is 1. So this one is 1/4 above this ABCD plane. This is 3/4 above ABCD plane. This is again 1/4 above ABCD plane, and this is again 3/4. So this represents the 2-dimensional projection of this particular figure. This is isometric view, this is 2-dimensional projection. So both are identical. So with the help of this, we will be able to explain how we can realize these 2 atom bases. Here this atom at the corner A and this 1/4 atom, they combine to form a basis. Here there is this one, if I mark like this, this is a basis. That is, there are 2 atoms. So this is not having, otherwise it is not allowed to be there, because no such lattice positions are there as far as this face-centered cube is concerned. Though this particular atom is attached to A and it is part of this A lattice site. So if we take this one, if this is 0, 0, 0, this will be 1/4, 1/4, 1/4. So I can mark it as this lattice or basis consists of 2 atoms which are in the position difference is 0, 0, 0 and 1/4, 1/4, 1/4. Now let us see these 2. If you take these 2, this one is at the vertical plane half unit above. This one is vertical distance 3/4 above. Therefore, if I call this one as 0, 0, 0, this one will be having again same x unit from here 1/4 distance, from here 1/4 distance, because this is half unit. So this is 1/4, this is 1/4, and this is 3/4 above, this is half unit above. So the difference is 1/4. Therefore, this will also be 1/4, 1/4, 1/4. If I call this as 0, then combine these 2, again this is one and the same. Therefore, this is another basis. Basis consists of 2 atoms. Similarly, if I connect these 2, this is on the face center, on the bottom face ABCD. So this, if I call 0, 0, 0, this will be again 1/4, 1/4 and 1/4 above. So that this is also 1/4, 1/4, 1/4. So these together, this will also form a basis. Same way we can visualize this one. This one is half. So if I call this as 0, 0, 0, this will be 1/4, 1/4, and this is 3/4 above, means with respect to this is only 1/4 above. So this is 1/4, 1/4, 1/4. So combined, this will form another basis. So these are all bases which consist of 2 atoms. So 2 atom bases which are attached to this lattice point. This one is attached to this lattice point. This one is attached to this lattice point. This one is attached to this lattice point. Similarly, if you take this one, there will be another atom here. So you will be having a basis. There will be another atom here. So they will be having a basis. So you will be having many basis atoms. All basis atoms will be having, or basis consists of 2 atoms each. So like that, diamond cubic crystal structure will be formed.